So today we will continue sets. So first is types of set or some standard sets. So first is empty set. As there is an number 0, so for similar concept is there for the sets, means empty set is a set so empty set empty set is a set. Empty set is a set that has no element. So empty set has no elements. It is also called void set or null set. And how it is denoted? It is denoted by phi. This is an Greek letter, okay? So it is denoted by phi. And in the set notation, empty set is denoted by like this. In the set notation, how we denote sets? Within two curly brackets, right? We denote sets in two curly brackets, and for the empty set, these two curly brackets, and inside the curly brackets there is nothing. This means this is an empty set. Okay, yes. So now next is, this is like empty set, and after that universal set. Universal set. So when you solve an example or any problem in that includes sets, so there will be, there is a set for a particular problem, for a particular problem which contains all the elements required. That means if you are solving any quadratic equation, like, so suppose there is a quadratic equation, x square minus 4x plus 5, like this. This is a quadratic equation, and for this equation has solution in R, so it has solution in real number. So for this, real number is the universal set, and from this set of real numbers you have only two solution. Suppose that is 5 and minus 1. So these two are the solution of this quadratic equation, and this is the solution set like this, and these two elements belongs to R. So R is the universal set because R contains the solution of this equation, and for this problem R is the solution set, and every another problem you can have another universal set. So now some examples of empty set. Let us take some examples of empty set. So examples. So like, so take x belongs to natural number. Say x is a natural number. X such that x is a natural number and x is between 2 and 1. Say, is there any element in this set? So this has no element because the first natural number is 1 and the second natural number is 2. In between there is no natural number. So this set is 5, or this. This is an popular example. So let us take another example. So x such that x square plus 1 equal to 0 and x belongs to R. So tell me, is this set empty or not? So this set is also empty because for all x belongs to real numbers, x square is greater than equal to 0. So x square is never minus 1. That means x square plus 1 is never equal to 0. That means this set is empty. Okay. Now equal set. Equal sets. So two sets are said to be equal if they have exactly same elements. Okay. So so like this, x has that x is a root of, we can express the sets in different ways, but uh, they have exactly same elements. So this is a set builder form. X is a root of the equation. I am writing it in a set builder form. X square minus 5x plus 4, and this is a set, and we are writing b set as, what is the roots of this equation? 4 and 1. So 1 comma 4. Which representation of this set? B is in which representation? This is roster form and this is set builder form. So, but this is the expression of in different types, but these two sets are same, a equal to b, because 4 and 1 are the roots of this equation which belongs to a, and also b contains 1 and 4. So these two sets are equal. So next, singleton set. Singleton. Okay, singleton set. This type of set contains only one element. Okay, so for example we can take this example: x belongs to natural number and 1 less than x less than 3. So because this set has only one element, that is 2, because 2 is less than 3 and greater than 1, and 2 is a natural number, so this is an singleton set. Okay, so now cardinal number. So now cardinal numbers. Now cardinal numbers. Now cardinal numbers. So what is cardinal numbers? The number of elements. The number of elements present in a set called the cardinal number of the set, and it is denoted by either this or this. Okay, is the notation of the cardinal number of a set, of the cardinal number of the set A. So you can easily check that if a set has finite number of elements, then it is a finite set, and if it contains infinite number of elements, infinite number of elements, then it is an infinite set. Infinite set. Okay, so for example, let us take a is equal to x such that x belongs to natural number and x is less than 100. Okay, so you can see that the set A is equal to like this: 1 2 3 4 dot 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 up to 100, sorry, 99, up to 99. So it has 99 element. You can, it is an finite number. Okay, so it is an finite set. And if we take a equal to, oh sorry, b, and if we take b equal to the natural number, the set of natural number, so this is like this: 1 2 3 4 5 6 and dot dot dot, it is continuing. So this is an infinite set. Okay, right? So these are the two examples of infinite sets and then finite set. And another example, let us take c equal to x such that x belongs to real number and x is in between 0 and 1. This is also an infinite set. This is also an infinite set. Its cardinality is infinite. But this uh, this is an infinite set and also this is an infinite set. But these two are different. The cardinal number of these two set is different. Though these two are infinite set, but their cardinality is different. So if a set is infinite, that doesn't mean that its cardinality is infinite. But for a finite set, its cardinality is any number from the natural number. To be more precise, if a set is finite, then its cardinality is n, where n belongs to natural number. Okay, so there was a mathematician George Cantor who showed in his thesis paper that there are some hierarchy in the infinite sets. Like there are infinite numbers of elements in an infinite set which can be more or less than another infinite set. Okay, like R is an infinite set and also the rational number is an infinite set and also the natural number is an infinite set and also the integers an infinite set, but the cardinality of these four sets are different. Cardinality is different. Okay, next, equivalent set and equal sets. From this concept of cardinality, we can categorize sets into two ways: equal set and equivalent set. What is equivalent set? Equivalent sets. So equal set is cardinality of A is equal to cardinality of B and also the elements are same. Elements are exactly same. I have already said about the equal sets. And the equivalent set are that set for two sets is said to be equivalent if their cardinal number is same. Okay, so for equal sets, the cardinal number of the sets must be equal and also the elements must be same. But for equivalent set, the only criteria is the cardinality of the sets is equal. Okay, so next concept is subsets. So till now we have seen what is sets and description of sets. After that, some types of sets. So here the end of the introduction to sets. Now the concept of subsets. Okay, so as we do, let us take some example. Okay, let age a set and age consists of 1 2 3 4 5, and let take another set B such that B consists of 1 2 3 4 5, 6, 7, 8, 9, 10. So now can you see some relation between A and B? See that every element of A, 1 is an element of A, it is in B, 2 is in B, 3 is in B, 4 is in B, and 5 is also in B. So every element of A is an element of B. And furthermore, observe that B contains such elements which is not present in A. Okay, so for this scenario, we say that A is a subset of B. What does it means? It implies that this sign is implies that this sign means implies that. So implies that A is a subset of B means for all X belongs to A, implies X belongs to B. Okay, I am not saying that for all X belongs to B, X belongs to A. I am saying that for all X belongs to A, X belongs to B. That means every element of A is in B, but the converse is not true. That there is some element in B which are not present in A. So for this case, A is a subset of B, and this is the notation of proper subset. Proper subset means proper subset. So proper subset means there is an element, at least one element that is in B which is not in A. That means there exist Y belongs to B such that Y does not belongs to A. For this, A is a subset of B. Okay, A is a proper subset of B. And also this is another notation. This means B is superset of A. Superset of A, or B contains A. Both are same. B contains A. So these are equivalent statements, and if we denote like this, this is also subset of B. This includes the possibility that A is a subset of B, or A, we are not writing here proper subset because here the possibility that here may be A equal to B. Okay, this is why this equal sign is there. Okay, so remember a trick, that whenever we show whenever we are to show that two sets are equal, two sets are equal then we show that A is subset of B and B is subset of A. These two implies that A is equal to B. Always remember this. Okay. Okay. Next. So here we have introduced the notion of subset. So we can again introduce the universal set. So now universal set. So when we are working with too many sets, okay, let us consider there is set A, B, C, D, dot dot dot. Okay, there are so many sets up to I. There are so many sets we are working with. We are working with these sets. So when we say U is an universal set, U is an universal set. That means A is subset of U, B is subset of U, C is subset of U, D is subset of U, dot dot dot, I is also subset of U. So we are working with these sets and there is no other set except these. Then if U is the superset of these, all of these sets, then U is said to be the universal set. So we cannot go beyond the universal set for this particular problem while working these all these sets. Okay, so like example, for example, when we take some linear equations, i.e. straight lines. Okay, so let us take a straight line, some 2x plus 3y equal to 5. This is a straight line. Okay, this is a straight line, and for this straight line and another straight line, this is a family of straight line, ax plus by equal to c. This is a family of straight line. For this, the set, the universal set is, for these straight lines, the universal set is, what is the universal set? Suppose the points on the straight line. Let us take the points on the straight line. Points on this straight line. And this is a family of straight lines. So points on this straight line. Points on this family of straight lines. So for these points, what is the universal set? This is an equation of a straight line, and we are considering the points on this line, and this is an also a straight line. Okay, this is also a straight line. So again we are considering the points on this straight line. So for these two straight lines and the points on these two lines, what is the universal set? We are considering the points. That means these the points on this straight line are the subset of which? A subset of what? The points on this straight line are subset of what? So we are talking about the points on the straight line 2x plus 3y equal to 5. So tell me the points on this straight line are subset of larger set of points. And what is that? And what is that? Okay. So this is a Cartesian plane, and we are talking about this line. Let us take this is 2x plus 3y equal to 5. So we are considering these points on this straight line. So now tell me, these points are located where? Where is this pointer located? In this plane. In this plane. So this is the universal set. So for this set, the points on a 2D plane is the universal set. Okay? Yes. So next concept is power set. So what is power set? The definition of power set is the set of all subsets of a set is called power set of the set. This set means this set. Okay. So let us take for an example, A is a set of 1, 2, 3. Now observe the notation carefully. So A set is this. A set consists of 3 elements, 1, 2 and 3. Now the power set is denoted by P of A. That means power set of A is denoted by P of A. That means power set of A, this is the set, because we write sets in curly brackets. So as P of A is a set, power set of A is a set. This is the power set of A. Power set of A. Thus all subset. The subsets of A. Which are the subsets of A? The subsets of A is this 1, this 2, this 3, and firstly 5. After that 1, 2, 2, 3, 1, 3 and 1, 2, 3. This and this. This is the set notation. This is the set notation. This curly bracket and this curly bracket in between. This is a set. So we put curly brackets from in the left side and the right side, and in between them these all are sets, and these sets are all are the subsets of A. Okay, so after a while we will come to the subsets of A. So for a time being, this is the definition, that the set of all subsets of a set is called power set of the set. Okay, so now we are taking some examples of a subset of A. So A is the set this 1, 2, 3. So now what are the subsets of this set A? Subsets of set A. What are the subsets of set A? So subset means, again we can say that B is a subset of A when for all x belongs to B implies x belongs to A, right? All the elements of B is in A, then only B is a subset of A. So now A has 3 elements. Okay, this is a well-known example, well-known theorem that phi is a subset of every set. Why? Why phi is a subset of every set? Because this is vacaciously true. Vacaciously means we cannot argue that, we cannot give any logic that phi is not a subset of every set. Because if phi is not a subset, then what does it mean? It means that there exists, this is the sign of there exist, okay? There exists an x belongs to phi such that x does not belongs to, let us take subset A, set A, only then phi is not a subset of A. If this happens, listen carefully, if this happens that there exists an element x which is in the set phi such that x is not in A, then phi is not a subset of A. But can we find an element in phi? But phi does not contains any element, does not contains any element. So we cannot find any x that is in phi so that x is in not A. So we cannot find such x. So that means phi is a subset of A for every set A. Okay, that means phi is a subset of every set. So now again our main problem, that A is this set 1, 2, 3 and the subset of A. So now here, so the subset of A is phi, we have already got phi is a subset of A, and let obviously every set is a subset of set A itself. This is also universally true because you can intuitively understand that A is a subset of A, and this is, as this is equal, so we have to put this equal sign. Okay, so these two are proved that phi is a subset of A and every set is subset of itself. Okay, now these two are trivial subsets, and now non-trivial subsets. Which are the non-trivial subsets? The non-trivial subsets are like A contains the element 1, 2 and 3. Let us first take one element at a time. So this is the set contains one element, this is a singleton set and it is a subset of A. Again singleton 2, again singleton 3 is a subset of A. Now take two elements at a time. So 1, 2 is a subset of A, 1, 3 is a subset of A, and lastly 2, 3 is a subset of A. Can we take any other element? If we take 3 elements at a time, that means the set A itself. Okay, so there are no other subsets of A. So total, what is the number of total subsets? Let this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. Okay, these 8 are 8 subsets. So from this we can arrive an formula that if this A is n, that means cardinality of A, that means n of A is n. Oh, sorry. Let us write it m. Then the number of subset of A is 2 to the power m, and the proof requires some concept from the binomial expansion, and when we will read the binomial expansion, then I will prove this theorem. Okay, that every set has the number of subsets of every set which has m elements is 2 to the power m. So now you can say that this is an observation that power set of A, the number of elements in power set of A is 2 to the power m, because the number of subsets is the element of the power set of A. So number of elements in power set of A is 2 to the power m, where n of A is equal to m.